Hey, did you catch that? The sound of the F1 seemed to be at a higher pitch when it was moving towards us than when it was moving away from us. No, that's not your mind playing with you. That's the Doppler's effect in action. The Doppler's effect essentially shows us the apparent change of the frequency of a wave in relation to an observer moving relative to the source of the wave. Don't worry, that was the longest definition I found on the internet. Here's a simple graphical representation. So let's say I'm walking and I stub my toe, which at this point happens to me at least 5 times a week.
They ask you how you are, you just have to say that you're fine when you're not really fine, but you just can't get into it because
Anyways, I start to scream. As you can see, when I'm at a constant position, the sound waves on both sides have the same distances between them, or they have the same frequency. But when I start to run in pain, something changes. Let's say I'm running towards the north and therefore away from the south. I produce one sound wave that is moving towards the north and one that's moving towards the south. Currently, they both are equidistant from my mouth or the source of the wave. They also travel at the same speed. Then, I move slightly towards the north and produce another two sound waves. This process repeats again and again and again until the production of sound waves stops. Now we can see that the sound waves traveling towards the north in the same direction as me are closer together than the sound waves moving towards the south. This is essentially their frequency and, in macro terms, their pitch. That's the Doppler's effect in a nutshell. In 1842, the Austrian physicist Christian Andreas Doppler proposed a new theory in which a person watching a source of waves would find an increase in frequency as it comes near him and a decrease in frequency as it goes away from him. It was an interesting theory but had yet to be proven. A few years later, a Dutch meteorologist, Bias Ballet, proved the theory using a moving train. Later on, Armand Fizeau applied the Doppler's effect to the electromagnetic spectrum. Light comprises of different colors, each of them signifying a different frequency. Therefore, a light source going away from or coming towards us will show the spectrum with a different shift to the red or blue side respectively. He also showed that one could find the speed of the source with the knowledge of the redshift formula, z is equal to v by c. Later in the early 20th century, Albert Einstein showed that redshift could also arise from the gravity of an object. Only recently, the Doppler's effect has been applied on theories of what the accretion disks of black holes actually look like. Essentially, according to this theory, along with gravitational lensing, which causes an image of the accretion disk's underside and far upper side, there's the effect of the Doppler's effect, which causes the light that's being emitted from the material moving towards us to have a higher frequency and thus be blue. And the light that's being emitted from the material moving away from us has a lower frequency and thus being red. It's a really interesting concept and in practicality is confusing for the bystander because the waves we are receiving will not be the same when we receive them as when they are released. Luckily, there is a formula that helps scientists gauge the Doppler change. Here it is. Massive, isn't it? Well, don't worry. I'll break it down for you. FO represents the frequency of the wave at the observer. Fs represents the frequency of the wave at the source. V represents the velocity of the wave. VO represents the velocity of the observer. And Vs, the velocity of the source. What about the plus minus signs? Well, first let's understand how they affect the formula. This is some simple mathematics. If the value of the numerator increases, the value of the fraction increases as well, and vice versa. Take an example as 2 by 4 and 3 by 4. If the value of the denominator increases, however, the value of the fraction decreases, and vice versa. Take as an example 1 by 2 and 1 by 3. Back to the formula. If we want to increase the final answer, we will have to increase the value of the fraction, which means we either increase the value of the numerator or decrease the value of the denominator, which means if the frequency is increasing, the VO must be positive or the VS must be negative. Now, if the frequency is decreasing, the VO must be negative or the VS must be positive. If both of them have velocity, we can find out the relative velocity and plug that into the formula instead. Here's a set of diagrams for you to understand this. Basically, if the source is moving towards the object, we will take a negative Vs. If the source is moving away from the object, we'll take a positive Vs. If the object is moving towards the source, we'll take a positive VO. And if the object is moving away from the source, we'll take a negative VO. Simple. Now I'll give you a simple sample problem. There's a car traveling east at 36 kilometers per hour. There's a person walking west at 5.4 kilometers per hour. The car starts honking. The frequency of the sound wave is 500 hertz, and it's traveling at a speed of 350 meters per second. What is the frequency of the sound waves heard by the person? First of all, we have to change all the values so that they have the standard units. I'll take meters per second instead of kilometers per hour. 5.4 kilometers per hour is 1.5 meters per second, and 36 kilometers per hour is 10 meters per second. Now let's plug these values into the formula. Since the car or the source is traveling towards the observer or the person, the Vs value would be negative. And since the observer is moving towards the car, the VO value would be positive. Beep boop bop, and we can find out that the person is hearing sound waves that are traveling at around the peak frequency of 515 Hz. Because of the versatility of this effect, the formula is being used in a variety of fields, from astronomy, gauging the movements of stars and planets, as well as on the road, with sensors that calculate the speeds of vehicles to catch overspeeders. Anyways, that's it for today. Bye, nerds.